Example 3.2.7, a 480 volt, 60 hertz, Y connected 6-pole synchronous generator is rated via the included capability curve. We're asked, can the generator supply a line current of 580 amps at 0.75 power factor lagging? What's the maximum amount of reactive power the generator can produce? And if the generator is supplying 250 kilowatts of real power, what's the maximum amount of reactive power that it can simultaneously provide? So we're switching gears a little bit here. Instead of dealing with frequency, we're dealing with ratings. And so capability curves basically tell us all the operating regions that a generator can operate in. So we have to operate this generator inside of this curve here. So we can't operate over here or down here. The generator can only be operated inside of this curve. So the curve sets the limits. Normally the generator should be operated within this area right here. Can be operated in this area or in this area. However, typically that is not done. So we're asked to interpret this curve, and really it's just this problem's not very difficult. It's just knowing how to read this. Can the generator supply a line current of 580 amps at 0.75 power factor? So capability curves don't tell you anything about current. They tell you about real power and reactive power. So we have to translate this information over into power information. Additionally, capability curves are given on a three-phase basis. So we have to convert that over to three-phase power information. So that's going to be the approach that we're going to take. So the givens here are that we have a line-to-line voltage of 480 volts. We have a frequency of 60 hertz. It is Y connected, and it has 6 poles. And I'll tell you, none of this matters. Really, all we need from the given statement is that. We are asked to find operating point. So where on the capability curve for 580 amps at 0.75 lagging. The maximum power that the generator can provide and the maximum reactive power at P equals 250 kilowatts. So the solution for this is first we need to translate this information into power. So P three-phase is going to be equal to 3 times the terminal voltage times the armature current times the cosine of the power factor. So that's 3 times 480 over root 3. We're asked if it can deliver 580 amps. That's per line. And cosine of, well, I didn't do that part. Cosine of theta is 0.75. So that gives us 361.7 kW. Then that gives us 1 point. That gives us the x-axis point. Here we still need to figure out the reactive portion. And Q three-phase is almost the same formula, 3 VT IA cosine of phi. Sorry, that would be exactly the same formula. Sine, right? This is a power triangle. So S phi, so P equals S cosine phi. Q equals magnitude of S sine phi. Just for clarification. So 3 times 480 over root 3 times 580, and then this would be 0.661. So what I did there is I took the inverse cosine of 0.75 and then just took the sine of that. So that's 318.9 kilovar. So that's this operating point is really asking us, can we deliver that much three-phase power? So what we need to do is find these 2 points on the capability curve. So we come over here and we find the first was 361.7. So, that's roughly right here. And then the second was 318.9. So, that's roughly right here. And it's positive because this was a lagging load. So I just need to draw a line here and draw another line here. And we see that indeed that point is outside of the capability curve. I really encourage you, I didn't do it on this laptop because it's difficult to do it, but on a piece of paper you can use a ruler to determine how long these are, and so you can get really accurate if you use rulers on these capability curves. So use a ruler to figure out, you know, how many watts an inch represents, and then convert that over onto your capability curve. So the answer is no, it can't. We're outside of the generator's operating range. So, no. The next question was, what's the maximum amount of reactive power that the generator can produce? So all generators, almost without exception, produce max power when the reactive power is 0. So reactive power is 0 is this axis right here. So we just find where the capability curve crosses that axis, and we see that that's, that's the maximum real power. This has maximum reactive power. Well, anyway, maximum real power is provided when Q is equal to 0. So if that was the question, I don't know, it would have been about 460 watts. What's the maximum amount of reactive power the generator can produce? Well, remember, generators produce positive reactive power. Where is this curve maximum? That's that point right there. So 375 kilovar, somewhere around there, is what I would say. Okay, so that's part B. And then in part C it asks, if the generator supplies 250 kilowatts of real power, what's the maximum amount of reactive power that can be supplied? So what we do then is we come over to 250 kilowatts. That's this axis right here. We just find where that intersects with the curve, which is that point. Just draw that over right there. So we need to know what that value is. And that's about, it's a little less than 350, so we'll say 340 kilovar. So that's about the max reactive power. We should be careful at that operating point, though. That's outside. That generator is really delivering a power factor that's lower than it should be. So that's outside of the generator's normal operating procedure. If you want to keep the generator within its rated conditions, we really should have stopped right here. So this is absolute max, and 200 right there is normal max. So we really do want to operate at this limit right here. Under most conditions, the generator is happiest. Under transient conditions, if we're only providing this in, say seconds or minutes at a time, this is fine. But for normal operating conditions, we want to be at 200 kilovar instead.